Okay, we're going to start this off. These questions are similar to what we did yesterday. I'm making my video now. Don't look at me. This is weird. We said if you want to find the slope of a function, in this particular case, 1 over x, at an x value, we need the point that's on the curve that we care about. So when x is 2, y is a half. But we also need a variable point, which I've been using the letter a. You can use whatever you want, but that represents any point on the curve that we care about. Okay? So the slope between them is 1 over a minus 1 over 2. That's y2 minus y1. That's what we're using here, right? y2 minus y1 over x2 minus x1 over a minus 2, like that. And we want to know what's going on as we let a approach 2. So we cannot handle this the way it is, because when you plug in 2, you get 0 over 0. So we need to get rid of these little fractions up here. And we're going to do that by multiplying by 2a to the numerator and the denominator. When you multiply this over here, you get 2 minus, when you multiply this into here, you get a over a minus 2 times 2a. And the limit as a goes to 2. These cross out, but they leave a negative 1 up here. So when you plug in, you get negative 1/4. Okay? Now, the tangent line to f of x equals 1 over x at 2 is the line. So when you graph 1 over x, it looks like this. Okay? At 2, so like 1, 2, we have this point right here, which is 2, 1/2. Tangent line is the line that this thing looks like if you zoom in on that point. Like, can you imagine if you zoomed in on that point right there, you'd see a line that kind of look like maybe that, if you zoomed in on that one little point. Okay, except it wouldn't be down there, it'd be right here. So let me change colors here to make this a little bit easier to see. If you zoomed in on that, it would look like that little red dash. Okay, but if you extend that as a line, you see this thing happening. So that is the equation that we're looking for, the line that thing looks like. But here's what we know. We know it has to go through the point 2, 1/2, and it has to have the slope of the function right there. Well, the slope of that function at 2 was negative 1/4. We already found that. So we need a line that has a slope of negative 1/4 but goes through this point. And we talked about yesterday, point slope form is y minus the y value equals the slope x minus the x value. And all I'm saying here is if you graph that line and that function, which I'm going to do for you right here. So again, the function we care about was 1 divided by x. It looks like that. The point we care about was 2, 1/2. So let's graph that. There it is. And the line was y minus 1/2 is equal to, nope, not there, dummy. Boom. Equal to negative 1/4 x. Let's keep me down there. Get out of that fraction there. There we go. X minus 2. Boom. And you can see in this picture here, let me change it here, but that green line just comes in, barely touches that red curve at that point, and if you zoom in on them, they look exactly the same. You can't even tell the difference between the green line or the green line or the red curve. Okay, that's what a tangent line is. It's a line that the curve looks like if you zoom way, way, way far into it. All right. So going back to here, extending our idea of slope and everything. So yesterday, we found the slope of x squared at x equals 1. Remember, that was 2. But we did that by, just like we did in the warm-up, we took the point we want, we took a variable point, and we determined the slope there. Okay. The notation for that we use is just what we used in the warm-up. A squared minus 1 over a minus 1. So, a squared minus 1 over a minus 1 reduces down to, that's the unsimplified version of that. Yesterday we saw if we factor and cancel, it reduces down to a plus 1. So this thing here and this thing here are equivalent. They're the same except for at 1. Okay? But if you graph a plus 1, if you graph the simplified version, it has a slope of 1 and a y-intercept of 1. So it looks like that, to the best of my ability. Okay? Which means if we graph the unsimplified version, right, if we don't simplify it and leave it, there's a hole in it. There's a hole at 1. And that hole is at 1, 2. It looks like this. Now I'm drawing the hole really big there so you can see it, but it's really just 1 point that we're taking out. So the hole was not really a gigantic thing like that. And I'll show you that on Desmos in a second. But that's what the unsimplified version looks like. The point of this being that both of those curves, as we plug in values of x closer to 1, the y values get closer to, on both sides, this hole here or this point right here. They both do the same thing. They both approach 2, which is why we define the slope at 1 to be 2. Okay. And I just have this little thing here to make sure we're all on the same page. We're not concerned with what's happening at 2 in this case. Okay, we're not concerned with what's going on at 2 because if you look at this picture, they're different. At 2 here, there's a hole, and at 2 here, there's an actual point. But that doesn't matter because the answer to both these questions is the same if we talk about the limit as we approach 1. Okay, so we're not worried about what's happening at x equals 1. I think I said 2, but I meant 1. We're concerned with what's happening around it. So there's a difference between where a function actually is, where it actually is at 1, and where a function is going. Okay? Where a function is, this is notated as f of 1. Where a function is going is notated as the limit as we approach 1 of f of x. They're different questions, although sometimes they have the same answer. Okay? So if we go through here, yeah, if we go through here, what's going on at 1? Yeah, at 1, you can see there's a hole here, right? Now there's a point way up here, but there's still a hole there. So what's happening is my function is approaching this hole, but the y value is actually way up here. So f of 1 is 5. Okay, but what's happening around 1 is the same thing as saying where is it headed as we approach 1. Okay, and that notation is right here. The limit as we approach 1 is actually 2, because the graph is headed towards that point 2. But the point is actually at 5. Okay. This function graph to the left, yeah, it doesn't mean anything. I just made that up. I have to make these weird little functions. But if you were to see like an easier limit, for instance, this one right down here, if you put a 2 into there, you get 10 plus 1, 11. All that means is on that graph, at 2, there's a point at 11. Okay? It actually just looks like this. And if there's a point there, then have to approach it. That's what's going on there. When we get to something crazy like this, now I'm asking what's happening at f of 3. But if you look at where x equals 3, there is no point. Nowhere on here, if you look at all the x equals 3, there's no point there. So what that means is f of 3 is actually undefined. It doesn't tell me what to do with 3. If there was a point up here, I would say f of 3 was 5. But there's not a point there. Okay? But what's happening around 3, we can still talk about what's going on as we get towards 3, as we move towards 3. So what's happening, though, in this particular case is this side here is approaching this y value, which is 3. And this side here is approaching this y value, which is 1. They're approaching different things, so we need notation to talk about different sides of an x value. So in this case, as we approach 3 from the left, that's this side down here. This is the left side of 3. It's headed towards the x value of 1. Okay, that's the notation for the left side. You put that little minus there. It looks like an exponent. It's called a superscript, but it's this little minus sign, and it means we only care about the left-hand side of 3. If there's a little plus there, that means we only care about the right-hand side of 3, which is here. We're headed towards 3, but on the right side. Well, that's headed towards the y value of 3. Now, because the left side and the right side are not approaching the same thing, the limit as x approaches 3. That means we got to look at both sides. Since they're not the same thing, we say that limit is dne. Yeah. Okay. So look, that's different than what happened way up here. Here, there's a hole there, right? There's a point way up here, but both sides are approaching that y value of 2. So the limit was 2. Because I'm checking both sides, they're both going to 2. Down here, both sides are going different places. So the left-hand limit exists, it's 1. The right-hand limit exists, it's 3. But because they're not the same, the limit at 3 is dne. Okay. So something I want to do for you guys for homework is just have you graph some of these and try to look at what the limit is without actually evaluating them, okay? So if we do that for the first one, again, what this question is asking you here is, if we approach 2, if I plug in values really close to 2, where the y value is going to be. Well, we can do that on Desmos. You can do it in a graphing calculator. It really doesn't matter. I'm going to use Desmos because I think it's a little bit simpler, but I'm just going to graph 3x plus 4. And this is an easy question, right? This isn't like a super difficult thing to do. Maybe you already know the answer without doing anything. But what I'm asking you is, what's going on as we approach 2? Well, Desmos is nice because I can actually put my pencil on the paper on this graph here, and you can see the y values, right? So as I head towards a y value or an x value of 2, 1.8, 1.9, blah, 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 you can see the x values are just approaching 10, right? And we actually get there. At 2, the y value is 10. That doesn't have to happen, though. It just has to approach something, and from both sides, it's headed towards 10. So the answer to this question is 10, and we could have gotten that just by plugging in 2, right? 3 times 2 plus 4 is 10. And again, that's the consequence of that being a line, which is pretty simple. If you plug in 2, you get 10, so it must approach 10. But if we look at example 2, it's a little more complicated. We've actually seen this limit before. But just to attack it graphically, you got to put it in parentheses here. So we need the numerator to be in parentheses. Then we need the denominator to be all down here by itself, also in parentheses. So that's the limit we're talking about, but I'm talking about the x value of 5. So again, with Desmos, put your cursor on here. You can move it. As I move my x value towards 5, look what happens at 5. We get undefined. There's a hole there. You can't see it when I move that point away because the hole is only 1 point, so they don't graph it like that. But as we get close to 5, you can see those y values are getting really, really close to what's going on. 10.04, 10. Undefined there, 9.997 on the other side. They're getting really, really close to 10. It looks like the graph should be 10 when I get to 5, but it's not. It's undefined there. It's hard to get that. Okay, but the limit is 10. Algebraically, we could have seen that because the top factors like that, the numerator factors like that, the denominator is that, and that crosses out. When you plug 5 into there, you get 10. Okay, but right now we're just worried about graphically. Number 3 is 4e to the x minus 4 over 3x. So let's graph that thing. No, get out of here. E to the x. There's that. Minus 4. Divided by. Is it just x? I forget already. Nope. 3x. Okay. So, and we're interested in what's happening at 0. You can see, look, it looks like a pretty nice little curve here going through 0. But if I try to graph what's going on at 0, or go to 0, there's a hole there. If I could get it. There we go. Okay, at 0, it's undefined. But where does it look like the graph is headed as I head towards 0? You can see these y values on both sides are approaching, look, 0.9, 1 point, what number is that? It's a weird number, 1.208. Okay, it's hard to tell what it is. So sometimes what we can do here too, with Desmos, you can do this on your calculator as well, is we can define this function as f of x. And then I can just plug values in close to 0 and see what it equals. So if I try to do f of 0, it's going to tell me undefined because there's no point there. But if I plug in f of 0.1, that's a comma. If I plug in f of 0.1, it's going to tell me 1.4. Okay, now that's kind of close to 0, but you can get closer. If I plug in 0.0001, it's going to tell me 1.333. If I plug in even closer, 0.0000001, 1.3333333. So what's really going on there? Again, let's go a little bit closer. 0.0000001. Oh, I went too close. There we go. Okay. That 1.333 is happening on both sides, actually. If we plug in a negative value, so f of negative 0.00000, oh, I missed a parenthesis. Negative 0.0000001. And it's still 1.333. Again, there's a little discrepancy between the values. And that's happening because, again, the numbers are so small, the computer has a little trouble dealing with it. But this is headed towards 1.3333333 repeating, which is really 4/3. So here's what that means. Again, if you plug in values closer and closer to 0, you're going to get numbers closer and closer and closer to 4/3. But you'll notice if you put 0 into here originally, you get 0 divided by 0, which means you do more work. Algebraically solving that's a little bit tougher. We're not going to worry about exponentials with limits right yet. Okay, but graphically we can handle it, so that's why that's on here. As we approach 0 for number 4, 3 sine x over 5x. Let's do that. So you want to make sure for calculus that we're in radians. Desmos has that feature in here. If you hit the little wrench, you can hit radians. Your calculator has it in mode. I forget the function that we're looking at already. 3 sine x over 5x. Okay. So we're going to do 3. Your functions are in this little function button here. I want sine of x. That's what sine looks like before I do anything else. And we're going to divide that by 5x. And my question is, what's going on as we approach 0? So I'm going to zoom in on it. You can see what's going on there. It looks like it's headed to 0.6 already without doing anything special. But if you zoom in, you move your point there, look at 0.599, 59999, and all of a sudden, boom, it's just 0.6. Okay, again, something we can check to make sure is we can do f of and just plug in values really close to it. And you can do this on a calculator a little bit easier too, but 0.00001, it's just going to say point. It's actually not 0.6. It's just so close to 0.6 that my computer can't tell the difference, so it just says 0.6. But graphically, that's what's happening. If you didn't graph it, you wouldn't know that, right? If you put 0 into here, you get 0 divided by 0, which says I don't know what's going on there. I don't know where the point is. But graphing it wise, we can see it's headed towards 0.6. All right, number 5. As we approach 5 of absolute value of x minus 5 over x minus 5. Now this seems weird because like x minus 5 without the absolute value over x minus 5 should just equal 1, right? But something funny happens when we drop that absolute value in there. So absolute value on here is in this function notation. No. Where's this little bar? Oh my gosh, it's right there. Absolute value of x minus 5. Boom. Divided by x minus 5. Now look at this weird graph. Look what happens. So this is the x value 5 right here, okay? And on this side, you can see no matter what x is, all these values are just negative 1. It's negative 1 the whole time. And when you get to 5, there's nothing there. I can't even get to it. It's undefined. On the right-hand side of things, though, the y value is always 1. And you can check this. Plug any number you want into this function. It will either spit out a 1 or negative 1. So when I do f of 8, it's just 1. But if I do f of negative 8, I get negative 1. That's happening because, think about this, if you put an 8 in there, you get the absolute value of 8 minus 5 over 8 minus 5. Well, that's just the absolute value of 3 over 3. That's just 1. But if I plug in something less than 5, look what happens. If I plug like a 2 into here, now I get the absolute value of negative 3 over 3 over negative 3. Well, that's 3 over negative 3. That's negative 1. So no matter what happens, these things are going to cancel. It's just on one side they're negative 1, and the other side they're positive 1. But because both sides of this graph at 5, remember here's 5, this graph does this, and then this side does this. Because they're not headed to the same side, we say this limit does not exist. All right. And then last but not least, this one's a little weird one. If you try to drop a 0 into here for 1 over x, you're going to get e to the 1 over 0. Now, that's different than 0 over 0, okay? So some weird's going on here. In general, dividing by 0 for us, like, for instance, if you graphed 4 over x minus 3, and you learned this last year, that means at 3 there's a vertical asymptote because it makes the denominator undefined. So what's happening with this graph, before I even get to it, I'm going to graph it on Desmos in a second, but I'll show you what's going on. It's because the exponent becomes 1 over 0, we end up getting, like, this becomes essentially either infinity or negative infinity. So it's either going to be e to the infinity or e to the negative infinity is what's going on. Well, e to the infinity is just e 2.7-ish times itself over and over and over again. If you keep multiplying by 2.7, that's going to go to infinity. E to the negative infinity is really 1 over e to the infinity. Well, that's 1 divided by a huge number, right? That's 1 divided by something gigantic. And if you keep dividing by a huge number, this thing is going to go to 0. So those are our options at this point because of that. And let's think a little further here. That little minus sign right there means I want to plug in values left of 0. So think about a number line. Here's 0. I want to plug in numbers down here, but I want to get closer. I want to plug in like 0.1 and 0.05 and 0.0001, but they're negative because they're below 0. So that means I'm going to have, just in the exponent, if you think about it, 1, get out of here, 1 divided by super tiny negative numbers, right? Well, 1 divided by super tiny negative numbers is a big negative number, right? Again, 1 divided by negative 0.0001 is negative 10,000. Okay? Nope. Negative 100,000. But either way, it's a huge number. So we're going to have e to a huge, big negative number, and this, you're going to see, is going to 0 on this side. So let's graph this, which is the whole point. That's what I want you to do anyway. I was trying to rationalize to you why we're getting what we're getting. But if we graph e to the 1 over x, look at this crazy graph. Okay, the question was, what's happening to the left side? Here it is. As I approach 0 on the left side, look where it's going. You can see it. My x values are getting close to 0, but they're negative, and the y values are getting close to 0. Okay, it never really gets there. It's going to be undefined there. Again, the computer says it's 0, but it's really not until, well, not until it never ever gets to 0. But you can see it's headed towards 0. On the right-hand side, as I get closer and closer to 0, the graph shoots off the page. It just goes up to infinity. But because I'm only asking about that left-hand side, I can say that the graph is going to get closer and closer and closer to 0 is the answer for that. All right, so for homework, I just want you to finish up the rest of these pages here. There's only 14 of them. You can use Desmos on your phone or a tablet or laptop, whatever you want to do. You can also use a TI like 83 or 84. I'm going to show you one of those real quick. Let's do one. Let's do number 10 here. Okay. So just to show you how to handle this on a TI 84, if it ever opens up. Come on, baby. There we go. Okay. If you want to find out what that limit is, you got a couple options. One way to handle it is just to put this into your calculator. So at x minus 2, the way you get absolute value is in math and over to number. That's the very first option, absolute value. And I'm going to put x minus 2 in there. All right. Now, a couple options that we can use here. We could, on the home screen, as went back home, go to vars, go over to y vars, and go into function and choose y1. That's what I just put that function. I want to know what's happening on the left side of 2. Well, a number on the left side of 2 would be like 1.9. So I can do that. It spits out a negative 1. Okay. If I want to get closer to 2, I can hit second, enter, and that just gives me the same thing I just typed. And I can put 1.99999. What you're going to see is it spits out a negative 1 everywhere. Okay. Another way to evaluate that is to make a table. If you go to second window, the x value I care about is 2. I'm going to make my table step. That's a little delta table thing here. I'm going to make it really small. 0.001. And then I'm going to hit second, graph. That's going to give me this table. And what you're going to see is you go, now we want numbers on the left side of 2 again. So that's like 1.996, 1.995. But you can see all these numbers over here are just -1. So as I move towards 2 on the x, my y values are all just -1. So the limit is -1. And last but not least, I think this is one of the harder ones to do here. You can graph this thing. The problem with graphing it is sometimes you got to worry about what your window is. So for this graph, a nice window, we care about 2, so I might go from 0 to 4. And my y, again, depending on where we're going to go from, I might go from like -2 to 2. When you graph it, there's the graph. So the left side and the right side are different, but I only care about that left side. And if you hit trace, that'll put you on the actual function. So now you can move a little cursor around and see what the y values are headed towards. But you can still see they're all -1 until I get to 2, and then it's going to say y equals nothing because it's undefined there. And once you cross that side, now they're all equal to 1.